All right, so this is where we left off last time. So the telescope size. Actually, let me back up just a little bit because I'm not sure if I had mentioned this before, and it is kind of important. A telescope is a light gathering tool. I mean, astronomers use light. Not just visible light; they use light, in the infrared, in the gamma region, radio region, and so forth. So, all right. So getting back to resolving power. Okay. So when you can distinguish two objects that are close together. Just think about the human eye, right? When you look at something and just any like two cars, let's say, and the two cars get further and further away. Well, let's say they're moving at the same speed. Eventually, they come to a point where the human eye really can't distinguish them between each. Whether one is a single object or really, they're two separate cars. So the point where you can still see that they're two separate cars is the resolving power. Okay. All right. The other thing that is also talked about is called resolution, and that has to do with the wavelength. So it's directly, you get a better resolution with wavelength, but it's inversely proportional to the size of the telescope. So really, you want a bigger telescope to get better resolution. All right. Let's see. So here's just to give you some different values of resolution. So this is what they're showing you is this first picture of this is Andromeda, actually. Not that that's important, but this is at 10 arc minutes. So this resolution would be 10 arc minutes. The next one is 1 arc minute. And then this one down here is the 2 hash marks mean arc seconds. So this is at 5 arc seconds, and then 1 arc second. With modern telescopes, I mean, really, the kind that you find on mountaintops, we can actually resolve to just fractions of a microsecond, really tiny fractions of a microsecond. Of an arc second, sorry. Like micro arc seconds is really what I meant to say. So one of the way that we are able to record images is using what are called CCDs, or charge coupling devices. And actually, what's the nice thing about a charge coupling device is it's very similar to the human eye as far as obviously it's electronics, so it's not similar in that sense, but it's affected by light in a very similar way that to what the human eye does. All right, so that's one of the reasons that we like them. Plus, they're relatively inexpensive nowadays. I mean, every cell phone has these things inside them. If you have a cell phone with a camera. All right, so and of course, over the years, we've been able to use computers to make images better and better and better, or sharper is a good is definitely a good thing. So get most of the telescopes, the vast majority of telescopes are on the surface of the Earth, and the atmosphere tends to blur images, right? There's molecules, the molecules of air moving around due to heat and various turbulences in the atmosphere, and so that's actually not a desirable thing. You want nice, sharp, clear images. All right, so what we've done, of course, as I already mentioned, is we put a lot of telescopes on mountains, and we do this all over the world. It turns out that if you're up, a couple of miles up into the atmosphere, you very quickly are over most of the atmosphere. Like most of the atmosphere is very close to the surface of the Earth, and then of course, it gets thinner and thinner the higher up you go. So we generally don't put telescopes on mountains that are, let's say over 20,000 feet, because it's hard to get up that high. Physically, if astronomers have to get up there, and so it makes things difficult. And of course, you have to build the thing up there. So that's kind of a pain. The other thing is the mountains can't be just anywhere. There's definitely been a preference towards deserts. Obviously, they're generally pretty far away from population centers, so the light pollution from cities is definitely decreased. Although that's not always the case. Like, for example, there were two telescopes, very famous telescopes, Mount Wilson north of Los Angeles and Mount Palomar south of Los Angeles. And as Los Angeles, and these were famous telescopes back in the 1920s and 30s and 40s. But as Los Angeles got more and more populated, the light pollution was just so bad that, really Mount Wilson is almost completely useless nowadays. It's more of like just a tourist attraction. And Mount Palomar is still used for actual, astronomy, actual scientific investigation, but it's definitely not as popular as some of these other sites that are around the world, like in Chile, the deserts of Chile, and of course Hawaii, the mountains of Hawaii, and there's other regions. There's some telescopes in Australia as well. All right. So what else can we do to basically make the images less fuzzy, less blurry, and so what happened, as technology grew from the 1990s, the CCD technology, we learned a way of dealing with the atmosphere and making what's called active optics. If you've ever seen, let's see, I think there's a picture of it. Yeah. Here's a good picture. So when a telescope sometimes we shoot a laser from a telescope, for distance to the moon, right? That's one way. But one thing that you do with a laser. But one of the main real reason that you have lasers shooting out of telescopes, and sometimes you'll see these pictures, is really all about what's called adaptive optics, or sometimes it's called active optics. And so what that does is telescopes that use this kind of thing will actually, there's like little how can I describe it? The mirror is supported by let's say little springs all over the mirror or underneath the mirror, and the springs can be either stretched or pushed apart, and what the laser is doing is it's basically lighting up the atmosphere and seeing what the turbulence is doing to the light, and so you already know you have a knowledge of what this light should look like when it hits the atmosphere, and then when that light comes back, the computers will change the positions of the mirror ever so slightly, this way, that way, this way, that way, and it will adjust so that the image is the image, from space is very clear. I mean, you're not interested in the light that's coming back from the from the from the laser hitting the atmosphere, but we use that to adjust the optics, right? Because the optics have to have to be adjusted for the atmosphere, right? So that's adaptive optics. That's very, very popular. All modern telescopes are built with adaptive optics. All right, so moving on. So here's, there's a very famous, I know this dish quite well, as a matter of fact. This is actually up in the mountains of West Virginia. This is called the Green Bank Radio Telescope. There's actually multiple radio telescopes up there. A wonderful part of the country, if you ever get the chance to go up to Green Bank. West Virginia. Anyhow, so the radio telescopes, and we have these all over the planet, are of course used to focus radio waves. This was actually discovered, I think it was like back in the 1940s, that objects in space can emit radio frequencies, and we have been observing these things for different objects for a very, very long time. You don't get, of course, with a radio telescope, you don't get a picture the same way you do with an optical, with a visible telescope. But what we can do is we take the different frequencies and you kind of make the different frequencies into, like, it's kind of like a color substitution. Like the longer frequencies would be more reddish, and the shorter frequencies more bluish, and you get kind of like a cartoon looking picture, basically, with radio astronomy. This is actually the largest radio telescope in the world. It's in Puerto Rico. It's called Arecibo. It's actually built into the side of a valley, and the problem with it is it can't be aimed other than the Earth moving, right? This doesn't, like, the telescopes up here can you can aim them, in any, almost any direction you want. This doesn't, you don't aim this thing at all. It just sits there, and whatever is directly overhead, that's what it sees. All right, so it's still used today, but nowadays these type of telescopes are really are used much more frequently, and lots of them that form what's called a large baseline. In fact, there's a huge, there's probably a picture of it right here. All right, so anyhow, so of course you get really poor resolution because they're much longer waves. But the nice thing about radio astronomy is you can look anytime. The sun can be out, it can be rainy, it can be, there can be clouds, there can be snow. There's nothing that prevents you from, observing in the radio region of the spectrum. And of course, radio waves pass through the atmosphere, as we've talked about before. So you're always able to do that. So this is the big thing this is really why radio telescopes are used, is what's called interferometry. So you can combine the signals from many different telescopes. So this is a good example. This picture right here is showing what's called the very large array, the VLA, and here's another picture of more closer look at these telescopes, and they're on railroad tracks, and they can be moved and separated at different distances for different types of experiments. And if essentially, however far the telescopes are apart, that gives you that's essentially effectively the diameter of the telescope.